Hello class, this is CSE 5720, section 2, week 13, fall 2025. I think we're ready to conclude our discussion on chapter 8. So, chapter 8 was a big chapter full of big scary notation and different normal forms, and in making this material, I had to do my best to make it as understandable as possible, even if it meant going against the textbook. Okay, so we are going to look at one more normal form. So let's recap everything we talked about by comparing Boy Scout normal form and third normal form. So Boy Scout normal form is a stricter version of third normal form, or put it another way, third normal form is a weaker version of Boy Scout normal form. So remember the schema that we had in the last video where we had a table of students, their advisors, and their departments? Where, for example, in here we have Instructor Einstein advising student Snow, Instructor Brandt advising students Shankar and Williams, and Instructor Mozart also advising student Williams. We tried to get this into Boy Scout normal form and failed. So we had to go for a different normal form that is third normal form. This is what it looked like when we tried to decompose this table into two schemas. The problem was this was not dependency preserving. In trying to maintain Boy Scout normal form, we lost this functional dependency. Student and department name determines instructor, or student ID and department name determines instructor ID, who is basically the advisor. So in this case, Boy Scout normal form does not preserve dependencies. We had to go for third normal form instead. So let's talk about that. So Boy Scout normal form and third normal form. Let's talk about our goals for database design with functional dependencies. So our goals, ideally, we want our schemas to be in Boy Scout normal form. We want our schemas to be lossless. We are basically breaking down schemas into smaller ones that we say are normalized. When we do so, it should be possible to recreate the original large schemas without any information loss. We saw an example of what it looks like for a decomposed schema to have information loss. We don't want that. We don't want lossy decomposition. We want lossless decomposition. Also, we want all our functional dependencies to hold. In the previous slide, this was an example of a decomposition that did not preserve dependencies. We don't want that either. However, the thing about Boy Scout normal form, as we've also seen here, it's not always possible for us to get to Boy Scout normal form. So we can't always satisfy the goal of B, C, and F. So we just go with third normal form instead. Alright, so here's what I mean about going against the textbook. So this chapter talks about first normal form, Boy Scout normal form, third normal form, and fourth normal form in that order. Which is a little bit weird, but don't worry about it. Also, it doesn't really talk about what dependencies we are working with, which I feel like is more important because each normal form deals with a different type of dependency. So, let's talk about all of them. Okay, so first normal form is basically administrative required. There isn't anything that we talk about for dependencies with that. So we're gonna skip straight to second normal form, which is not talked about in the book, weirdly enough, but I think it's a good idea to talk about second normal form anyway, because at least it's easy to understand what a partial dependency is. Suppose we have a schema that looks like this. So in here, we have the primary key attributes A and B. A and B determine C, but A by itself determines D. This is what's known as a partial dependency. In a relation schema, we want all non-key attributes to be determined by the entirety of the primary key, not a portion of it. If we can achieve that, we have second normal form. If we can't, that's a second normal form violation. So let me repeat. If a non-key attribute is determined by a portion of the primary key and not the whole primary key, that is a partial dependency. We have the whole key, we want to use the whole key. Even if we can't do that, we just break up the table into two smaller ones, for which the entire key is used to determine all non-key attributes. Second normal form prohibits partial dependencies. In this case, because A and B determine C, but only A determines D, we just break this up into two schemas where A, B, and C are the attributes of the first table, and A and D are the attributes of the second table. So here's another example. Okay, so here's another example. Suppose a relation schema has a primary key that determines a non-key attribute, and that attribute determines another non-key attribute. This isn't really talked about in the book, at least not all that well, but this is what is called a transitive dependency. If a non-key attribute is determined by another non-key attribute, which is itself determined by the primary key, that is a transitive dependency. If A determines B and A is the primary key, but B also determines C, that's a transitive dependency, and that is a third normal form violation. Third normal form prohibits transitive dependencies. By extension, so does Boyce-Codd normal form. Boyce-Codd normal form, as I talked about earlier, is a stronger form of third normal form. It has the additional requirement that the left-hand side of all functional dependencies to be superkeys. I call it the left-hand side, but in other resources, you might see the left-hand side be called by a different name. That is the determinant. Just so you know. Because in this schema, A determines B, but B also determines C, we split this table into two, where the primary key of the first table is A, and A determines B, and the primary key of the second table is B, and B determines C. We also have an algorithm for decomposing a non-BCNF schema into two that are, and if the schemas produced this way are not still in BCNF, we just keep decomposing until we get a set of schemas that are in BCNF. There's also a similar algorithm for third normal form in section 8.5.2. The textbook briefly says the textbook briefly says that this particular definition of third normal form is equivalent to the one that uses transitive dependencies. And now, we get to the last thing we're going to talk about in here. So we have partial dependencies, which second normal form gets rid of. Third normal form gets rid of transitive dependencies. And now, we get to multi-value dependencies. So, sometimes Boyce-Codd normal form is too much, but sometimes still, Boyce-Codd normal form is not enough. Okay, so, Boyce-Codd normal form is sometimes too much, Boyce-Codd normal form is sometimes not enough. So consider a schema, a variant of the instructor schema that allows for the following. An instructor can be associated with more than one department, which was a possibility when we were talking about the university database example all throughout the course. But we also include the possibility that an instructor could have more than one address. If it were the case that an instructor can only have one address, we could safely say that the ID by itself determines the name of the instructor, the instructor's address, which is the street and the city combined, and by extension also the department name. Because we allow for an instructor to have multiple addresses and be part of more than one department, we can no longer enforce the functional dependency ID determines street and city. Nor can we uphold the functional dependency ID determines department name. However, we would still like for ID determines name to be enforced. So let's look at our functional dependencies. So we have ID determines name, which holds because we still require that each instructor has one name in the database. But ID determines street and city, basically the address. That can't hold because in Boyce Codd normal form, the left-hand side of all these functional dependencies must be superkeys. And in this case, the ID is no longer enough information to uniquely identify each tuple. So Boyce Codd normal form says the left-hand side of every functional dependency for a relation schema must be a superkey. And if that isn't upheld, then we have a Boyce Codd normal form violation. In this case, ID is enough to determine the name, but ID is not enough to uniquely identify each row in the table. And the same is true for ID determines street and city and ID determines department name. We could decompose this schema into two schemas that are in BCNF following the procedure for decomposing such a schema. So, we have a functional dependency X determines Y that violates BCNF. So we can decompose it into two such schemas, R1 and R2, where the schema for R1 is the union of X and Y, and the schema for R2 is R minus X minus Y. In other words, we can simply separate this, we can decompose this one schema. So one is ID and name, and the other is ID and everything else. However, there's still a problem with this schema. Well, the first schema is perfectly fine because ID is enough information to uniquely identify each instructor's name. Even if it's possible that two different unrelated instructors could have the same name, we can fall back to the instructor ID to figure out who's who. But the problem is, we're still allowing instructors to have more than one address and be a part of more than one department. So consider the example of an instructor who is in more than one department and has more than one address. If we try to represent this instructor, we would have something that looks like this, where we have one instructor with two departments and two addresses, and we have to represent every possible combination of address and department. You might be looking at this and think to yourself, just separate the department name from the address, and you'd be right. We can do that. But we have to formalize how to do that. So we can keep decomposing this further until we get three schemas. One is ID and name, the second one is department name and ID, and the third one is ID, street, and city. What we need to do is formally describe how we decompose the second schema into two more, department name and ID, street, and city. To do that, we need to introduce the notion of multi-valued dependencies, and through that, we can introduce our fourth and final normal form. Okay, so what in the world is a multi-valued dependency? Normally, with the functional dependency A determines B, we disallow tuples where the same value for A can have different mappings for B. So if A1 determines B1, A1 cannot determine B2, A1 cannot determine B3. If it did, it would violate the definition of a function as a many-to-one mapping. With a multi-valued dependency, this can happen, and we denote such dependencies as A double arrow B. So here is the formal definition of a multi-valued dependency. Whoa, what's that? Let R be a resolution schema and alpha and beta be subsets of R. The multi-valued dependency alpha double arrow beta holds on R if in any legal instance for R, for all pairs of tuples T1 and T2 in R, such that T1 alpha equals T2 alpha, there exist two more tuples such that T1 alpha equals T2 alpha equals T3 alpha equals T4 alpha. T1 beta equals T3 beta. T3, okay, this is gonna get a little bit ridiculous. So I'm actually gonna give you a slightly easier to understand definition, even if it is not as precise as whatever this is. So this is the formal definition of a multi-valued dependency without any room for misinterpretation. I'll just describe it as this instead, and just put up these things on the side. So for any pair of tuples T1 and T2 that have the same value for alpha, there are two more tuples in T3 called T3 and T4, such that all four tuples have the same value for alpha. T1 and T3 have the same value for beta. T2 and T3 have the same values for all other attributes. I'm going to describe R minus beta as all other attributes. That's not as precise, but it's probably a little bit easier to understand. T2 and T3 have the same value for beta, and T1 and T4 all have the same value for all other attributes. You might still be lost in this one, and here is a visual of what's going on. So here's a simplified example with three attributes such that A and B correspond to alpha and beta, and A and B are single attributes. C, which technically corresponds to R minus beta minus alpha, are all other attributes. However, do note that in the general case, alpha and beta may be multiple attributes, and all other attributes may also be multiple attributes in and of itself. So, in the simplified case where alpha, beta, and all other attributes are all singular attributes, for any pair of tuples T1 and T2 with the same value for A, there exists two more tuples T3 and T4, such that all four tuples have the same value for A. Tuples T1 and T3 have the same value for B. Tuples T2 and T3 have the same value for C. Tuples T2 and T4 have the same value for B. Tuples T1 and T4 have the same value for C. Do you see what's going on here? We have values for B and C. Two different values for B and C each, B1 and B2 for B, and C1 and C2 for C. Basically, there are four tuples for which the value for A is all the same, but the values for B and C is basically every possible combination of B1 and B2 with C1 and C2. So B1, C1, B2, C2, B1, C2, and B2, C1. This is what's going on when we have a multi-valued dependency. If we have four tuples like this, that's a multi-valued dependency. And that also must hold for every possible pair of tuples. And that is the definition of a multi-valued dependency. If you can understand the notion of this all possible combinations mixing, which I believe that's a Cartesian product of B1 and B2 with C1 and C2, then you basically have the grain of knowledge to understand that, okay, this is what's going on with the multi-valued dependency. So, there are two values, as I said, there are two values for B and C, B1 and C2, and C1 and C2. And these four tuples basically contain every possible combination of B and C. And this is what a multi-valued dependency is describing. For a pair of tuples, there is another pair of tuples that basically represents every possible combination as visualized here. So here is the same example with our departments and addresses. See how there's two values for department name and address? And see how there are four different combinations for the two values of department name and address? So computer science and street, some town. Electrical engineering, street, some town. Computer science, road, some city. Electrical engineering, road, some city. Here's another instance where we have here's another instance that we're going to use to look at the difference between a functional dependency and a multi-valued dependency. So notice how 22222 physics is repeated for each address. So this is an instance where one instructor is part of one department but has two addresses. This is because for each instructor ID, we must repeat department name for each street city combination and vice versa. For every department, we have to repeat that for each address. For each address, we have to repeat that for each department. So that's how we get that every possible combinations thing going on in the previous slides. This also means if we did something like this is illegal. In other words, we want every tuple combination for department name and street city. So in this instance, we actually have stuff missing. That is physics North Rye, which is present. We need all four of these. Physics North Rye, which is present. Physics Main Manchester, which is missing. Math North Rye, which is missing. And Math Main Manchester, which is present. So this is an illegal instance. We need every possible combination. Since department name and address are two unrelated or rather independent things, we say that this repetition is unnecessary. But for a multi-value dependency, we actually want this. And we can denote this as ID double arrow street and city and ID double arrow department name. Remember when we talked about the closure of a set of functional dependencies a while back? Well, much like how we can find the closure for a set of functional dependencies F, and the closure is denoted as F plus, we can do the same for a set of functional and multi-valued dependencies. We call the set D, and we call the closure of that set D plus. We're not going to go through all the rules of inference for multi-valued dependencies, but three of them are actually based on the three Armstrong's axioms. Those are the reflexivity rule, augmentation rule, and transitivity rule. Also, if you have a functional dependency, that's also a multi-valued dependency. If A determines beta, then A double arrow beta. This is called the replication rule. Also, there's another rule. If A double arrow B, then A double arrow R minus. Okay, if alpha double arrow beta, then alpha double arrow R minus alpha minus beta. This is called the complementation rule. There are more such rules in Appendix B. Appendix B is not part of the book. It's linked. It's on the book's website. I linked that in the slides. And now we can finally look at the definition of fourth normal form. A relation schema R is in fourth normal form with respect to a set of functional and multi-valued dependencies D if for all such dependencies in D plus of the form alpha and double arrow beta and alpha and beta are subsets of R, at least one of these holds. Alpha double arrow beta is a trivial multi-valued dependency, or I think I wrote this wrong. Or alpha is a superkey of R. Yeah, this was wrong. Hold on. There we go. So, yeah. So, this is a long-winded way of saying fourth normal form prohibits multi-value dependencies. If we have this going on in our tables, where we have 4 tuples, where all of them have the same value for A, and they have every possible combination of 2 different values for B and C. If we have this crisscross applesauce going on here, that is a fourth normal form violation. Also, note that the textbook defined Boyce-Codd normal form and third normal form in a way that doesn't talk about functional dependencies. And note that the definition for fourth normal form looks like that for BC and F, except we're dealing with multi-value dependencies. It means that by extension, the decomposition algorithm for fourth normal form is actually identical to that of Boyce-Codd normal form, except it, of course, uses multi-value dependencies. For a schema R with a multi-value dependency x double arrow y that violates fourth normal form, but not Boyce-Codd normal form, we can split R into 2 schemas, R1, whose schema is the union of x and y, and R2, whose schema is R minus x minus y. For this example, we saw that ID double arrow department name and ID double arrow street and city. In either case, the ID is not a superkey because it's not enough information to uniquely identify each row in this table. So, if ID double arrow department name and ID double arrow street and city, and ID is not a superkey, ID is not enough to uniquely identify each row in this table, we have a fourth normal form violation. And as I said, department name and address are 2 separate things. Why don't we just separate it? And yeah, we can do that. So, without thinking about it too much, we can deduce that we should have a table for department name, and we should have a table for addresses. But we also need to include for both tables the ID, so we know whose ID matches with what departments and addresses. So without thinking about it too much, hold on. Okay, as I said, without having to think about it too much, we can see that the department name and the address are 2 separate things. In a more complex example, you could just have one offending multi-value dependency that you would just separate from the rest of the schema. It's just that we have 2 such multi-value dependencies, so it doesn't matter which one we start with. So we're going to have to split this no matter what. So we're going to have 2 new schemas. One is ID and department name, and the other one is the 2 attributes that make up the address, so street and city. In fact, we can see a little hint of what it looks like, though without the ID. So we can see that we're going to have a table that has computer science and electrical engineering, and another table that's going to have street, some town, and road, some city. So here's what it looks like to have those 2 schemas separated from the original. So I guess a good question is this: what is the primary key for these 2? Well, for the multi-value dependency ID double arrow department name and ID double arrow street and city, it was not enough information to uniquely the ID was not enough information to uniquely identify each row in the original table, but it's still not enough for these 2 separated tables. So it turns out the primary key is all the attributes. So ID and department name is the primary key for this upper table here, and the ID, street, and city is the primary key for this lower table down here. So, we have hit the quote-unquote end of Chapter 8. So, when it comes to database design, we would like our schemas to be normalized. We want our schemas to be normalized. And the goal, the idea behind normalization is to reduce duplicate data and also prevent anomalies with insertions, deletions, and updates, but also make it easier for the database to maintain. We would also like the size of our schemas to be just right. We mentioned that earlier in Chapter 8, but it took us a long while to define what it means to be just right. We don't want them too big because we'd have redundant information, and if it is too big, we saw various normal forms in which if a schema violates one of those normal forms, we just split it into two schemas, and we keep splitting it until it violates no more normal forms. However, we don't want to go too far either, because if we did, we get lossy decomposition. We don't want that either. And we know when to split a schema into two or more schemas by looking at its functional dependencies. So, and this is just a reiteration of our 3 design goals for database design. If a schema must be decomposed into smaller schemas, it should be done so losslessly. In other words, if we break up a schema into smaller schemas, it should be possible to recreate the original schema using a natural join operation, or for example. That's number 1. Number 2, all functional dependencies for each schema must also hold. If you have a schema and a functional dependency that involves 4 attributes, but your schema only has 3, that functional dependency no longer holds on that schema. So you want all your functional dependencies to hold. Ideally, and number 3, ideally, you want every schema to be in Boyce Codd normal form. But that's not always easy, that's not always achievable. And even if it is achievable, it might not always be enough. If you can't get to Boyce Codd normal form, then go with 3rd normal form instead. If Boyce Codd normal form is not enough, then aim for 4th normal form. We looked at various normal forms, each one stricter than the last. The first one is 1st normal form, which basically says atomicity. The domains of all your attributes must be atomic. If you have a column that basically represents 2 or more smaller attributes, give each of those component attributes its own column. If you have a cell that has 2 values for 1 attribute, you give each of those attributes its own row. That's 1st normal form. 2nd normal form is not talked about in the book at all, but it basically says eliminate partial dependencies. 3rd normal form, although 3rd normal form is not defined in terms of transitive dependencies, it eliminates transitive dependencies. Boyce Codd normal form is a stricter version of that requires the left-hand side of each functional dependency for a schema to be also a superkey. And 4th normal form eliminates multi-value dependencies. So, 2nd, 3rd, and 4th normal form eliminate different types of dependencies. But that isn't even the final normal form. There are even more normal forms that we talked about briefly earlier in this chapter, such as 5th normal form. If you have a table that was decomposed into smaller tables, you can reconstruct the original big table without information loss. That is 5th normal form, also known as projection join normal form. And the other one is called domain key normal form. That says all constraints and dependencies in a database can be enforced solely by enforcing domain constraints and key constraints. These 2 normal forms are discussed briefly in section 8.7, but even those are not the final normal forms. There are even more beyond those. There's even a sixth normal form, apparently. However, for our purposes, going beyond fourth normal form is overkill. In practice, it's hard to achieve any normal form beyond fourth normal form. So for our purposes, fifth normal form and beyond, that's just overkill. Sometimes it's possible to go too far with normalization. So, normalization is where we take a large schema and break it up into smaller schemas. The advantages of doing so is that it's easier to maintain data consistency. We also eliminate redundant data. However, sometimes because you are breaking up a table into smaller tables, if you want that original large table, you have to perform join operations to get that large table back. If it is expensive to do those join operations, if it is more expensive to do those join operations than it is to maintain consistency with redundant data, then you have justification to leave it unnormalized. If normalization involves splitting schemas, then denormalization is the process of recombining schemas that were already normalized. Again, why would you want to do this? Why would you want to go and undo all this normalization? Because sometimes it's just easier to maintain unnormalized data because joining might be more expensive. Joining might not be worth the cost. No, joining might be more expensive than it is to maintain redundant data. And this is something that also cycles back to what is called a materialized form. We defined a view to be, quote unquote, a query that pretends to be a table. There are a few cases where we want a materialized view. When you perform a query with a view is when that view is when the view so when you perform a query with a view is when that query associated with that view is actually computed. Sometimes you actually want to keep a cached copy of the table produced that way. So that way, when you compute it again, when you need that materialized view again, you don't have to recompute it again. This has the cost of, okay, now we have to save this materialized view and we have to perform view maintenance to make sure it doesn't become out of date. The thing is, sometimes you want that if the performance gains outweigh the cost of maintaining the view and with denormalization. With denormalization, sometimes it is justified to leave schemas denormalized or unnormalized if leaving it that way somehow makes queries be processed faster. So, we can normalize a schema, but it's also possible to go too far and we have to go back. So yeah, that's everything that I wanted to talk about in Chapter 8. So the final two chapters for the course are going to be Chapters 9 and 10. I'm just going to talk about those on a general level for the remainder of the course, and after that, it's going to be your final. So what I have in mind for your final is, well, you are going to take the set of schemas that you produced from your midterm and create a set of sample data that would populate each of those schemas. So I'll have further details around week 15. I might also require you to verify that your schemas are at least in third normal form, and if applicable, fourth normal form. So yeah, that's gonna be the remainder of the course. So with that, this is gonna be our conclusion to Chapter 8. We looked at We looked at functional dependencies, the rules of inference related to functional dependencies. We looked at 4 or 5 different normal forms. And yeah, that's going to be it on Chapter 8. So everything we talked about in Chapter 8 cycles back to how to design a good database. And also defining what a good database even is. There's even more in Chapter 8 that I did not even get to discuss. I just wanted to finish up Chapter 8 as soon as possible. Alright, so that's it. So that's it on Chapter 8. So I'm going to upload it as soon as possible. And yeah. Chapters 9 and 10, I'm just going to talk about those in a more general sense. And yeah, that's going to be it for the entire course. Alright, see you for the next video.